In this assignment, we will analyze point cloud and create high-resolution digital elevation models. After starting GRASS, let's create a new map set. I will call mine Assignment 5. And let's change to a working directory where we will download external data and where we will store our results. And here I will create again a new folder for homework 5. And change to it. Now let's download the provided lidar data and an orthophoto. And I recommend that you download them one by one so that you don't have troubles with zipping, unzipping to a different directory and other potential problems with a zipped file. So let's go to our current directory. Let's put the last file there, as well as the orthophoto. And the metadata for the orthophoto. And to check whether the lidar import works on your computer, you can just run the r/in-lidar command with --help, which gives you the help page for the command, and you can see all the options that are there. So we will start with analyzing the point cloud that we have. If you want to see a header of that point cloud, you can run /info tile on your LIS file. I will skip it and I will go directly into importing the tile. So first, we will import just the background points, and these background points have class number 2, so class filter. So we will apply v/in-lidar with class filter equal to. Now, if you get an error message that the projection information doesn't doesn't agree with your project coordinate system, then just run this command with -o flag. So let's now import the first return data. So now we are filtering with return number, return filter parameter. So it will be many more points because the first return has many more points than the background data. And as you can see, it takes quite a bit of time to render those points. So what we will do, we will rasterize this data, and to explore how dense the data are, we will compute the number of points per grid cell. And we will set the size of the cell to 1 meter. So the first step will be to set the region. So we will set the region to our point cloud, so to the vector file, spatial extent of the vector file, and resolution 1. So that's that's not a big tile. It's 700 meters times 700 meters. So it should be pretty easy to handle. And then when we will be importing the data and computing the number of points per each grid cell, we will be running it for this region. So let me run this. And then we will zoom to region to look at those files. So we computed number of bare ground points for each 1 meter grid cell. Now we will compute number of first return points for each grid cell. And then now I want to zoom to computational region, but you might have seen that the points took quite a bit of time to render. So I will switch off my point file and I will keep just the raster file. And now I will zoom in because that will be very quick. And you can see that the color table is not the best for the data that we have. So let's just change the color tables. And as you can see here, I can change the color table for both of the imported rasters at once with a single command. So I'm changing it for the bare ground point density and for first return point density. And I am assigning the blue, cyan, yellow, red ramp with histogram equalization. So now we can see much better the spatial distribution of the points. And this is the first return data. You can see that it's pretty complex. So let's now create some output maps for our report. So I will just erase everything and then bring it back in a clean way. So this is our bare ground data. And let's look at the legend to see how many points we have there. So we can now change that legend, and it would be useful also to add a scale bar. So you can see that it's close to 500 meters. It's about 700 meters region, so pretty small area. And you can see that most of the bare ground data really have mostly either no points, so those are these blue areas, and you can think about like what these blue areas are where we don't have any bare ground lidar points. And the rest of the areas have 1 or 2 points, and there are some grid cells that have more than 2 points. Let's now look at some statistics about how many grid cells actually have those points. So we have 36% with no points, so quite a big portion of our grid cells doesn't have any points at all. 37% have just 1 point, and there are almost no grid cells that have more than 4 points. And we can also run some statistics. So this just confirms you that the point density is relatively low, and there is essentially less than 1 point per each grid cell at 1 meter resolution. So let's just save that map for our report. And let's look at the first return data. Now you can see that this is a very different pattern. You can think about what these orange areas are, and when you think about how the lidar data are collected, they are collected in swaths, and these swaths have overlaps. So we have these high point density areas in the area of swath overlap. So let's look at how the legend actually looks like. So let's remove this one. Mm-hmm. And for this legend, we have included the histogram. Let's see whether it will show up. If we do it this way, yes. So you can see that there are few grid cells that have over 60 points per grid cell, very, very high density, but most of the grid cells have really between 0 and maybe 5 points per grid cell. And you can see that these high densities of points are really mostly at the edges of these swath overlaps. These overlaps need to be cleaned up when you are doing the processing, and you can see, you might have seen that in the previous maps we didn't have these overlaps because the background lidar point cloud is already filtered. So it is important to be aware that you have these high density swath overlaps. They may be shifted in the first return data. So let's look at how the distribution actually looks like. So we can see that these higher densities are in very, very few cells. This is percent cover. And most of the grid cells have 1, 2, maybe 3 points. So again, it's not that dense, and there are only very few cells that have higher point density, mostly in this swath overlap area. Here is the univariate statistics. Again, the range is very high, but the mean is around those 2 points. So let's now output this map for our report. So now what we can do, we can try to compute the digital elevation model for this area we already know that for the bare earth, we won't have coverage for every grid point, but for every grid cell, but we can get an idea about the spatial distributions of elevations just by binning, just by computing the mean elevation for each grid cell. So with this command, we are reading in the point cloud, and for each grid cell, we compute the mean elevation. And we will do it for bare ground point cloud and for first return point cloud. So this is the mean for the bare ground data. This is the mean for first return. And again, the color table is not ideal. Let me remove the legend. So we will change the color table to elevation, and the other one as well. And because they have quite a few no data cells, we will display them and create the maps separately. But first, let's look at the information about the first return data, because we have the colors, like you may remember that the colors for elevation go from bluish, greenish colors to brown, orange colors, and we don't see those orange colors here. So we want to see what's going on, what is the range of elevations there. And you can see, like in this in the first return data, we have the range of elevation from 77 meters to 700 meters, which is very different from what we have for the bare earth data. So let's create the maps. Let's see what's going on. So this is our bare earth DEM. You can see because we don't have the elevation, the lidar points for every grid cells. Many grid cells are missing points at 1 meter resolution. This is not a continuous field DEM. We have many no data cells, but we can see approximately how the elevations look like, and we can also see some of the topographic features. So let's look at how what is the range of elevation, how the elevations actually look like here. I will put my legend here. So the elevations for the bare ground are between 77 meters and 115 meters. And let's save this map for our report. Now, I will again erase this map, display the map for the first return data, and let's display the legend for the first return data. And I will keep the legend for the bare ground data for reference and for comparison. And you can see that in this case, the elevation in this first return actually is between those 77, maybe 200 meters. And we have somewhere some grid cells, or maybe just one grid cell, that is way above that elevation, that would indicate a feature, unrealistic feature of more than 500 meters high. So that should tell you that there is something going on, that there may be a point that shouldn't be there. So let's just save this map for our report again. And let's now change the region to 2-meter resolution and see whether we can use the binning to create a continuous 2-meter resolution DEM. So essentially here we are doing the same as before, but now at 2-meter resolution to see whether that will be whether with 2-meter resolution, we will get a continuous usable digital elevation model. So we can go, because this is the same, so we change the region, we keep the spatial extent, and we just change the resolution. And we just go through the same procedure. You can already see that it looks a little bit better for the bare ground. This is the first return. We still have that problem with some value being way out of range. What would you expect? We will change the color table to elevation. And let's just create maps for our report so that we can compare. So the legend for the bare ground is essentially the same. So we can just remove this one and keep that one. Oops. If this happens, you can easily get back by zooming to computational region. So let's just, let me get rid of this one. And let's just save this for our report so you can comment on that with 2-meter resolution, we are getting a better representation of bare ground, but we still have way too many cells without any data, without any elevation. And how does the first return look like? Again, it's a little bit better. Instead of 700 meters, we have 258 meters. Just put it here. And I will keep both for comparison. So we still have there an issue with a point that shouldn't be there. And let's just save this. And what I would like to recommend you is at this point to look at the lecture to find an explanation for what we have, what is the issue with that, with the first return data, that we have these very high values there and why those very high values are there. You can also switch to 3D and display that data in 3D. That will really show you what's going on, and that's the best to do it at 1-meter resolution. But you will still see it in this first return DEM as well. So make sure that you answer the question here. So now let's look at the range of values within each grid cell. That will tell you whether you have any above ground features in that location or whether it's mostly bare ground. So now, again, these are very simple raster procedures, but they give you a lot of information about the data and about the features that are captured by the data. Some of this is being done directly from the point cloud, but I found that doing them with raster analysis is much simpler and as efficient and as effective as when you do it with point cloud data, because you already have pre-processed the data on the fly. So now what we will do for each grid cell, we will compute the difference between minimum and maximum elevation for the point in that grid cell. And if there is just one point, it will be 0. So let's first do it for bare Earth, a point cloud. And then we will change the color scheme so that we can understand what is there. So what you would see here is, let me switch off this one. Again, like where there are zeros, we don't or where there is no data, it keeps the no data. And where you have some data, that data is the difference between the minimum and maximum elevation. And then we will comment on it once we display it with the legend. So let's now run it for the first return data. Again, change the color table to something more meaningful. Very different. So you can see that in the first return data, the range of values is has a very different spatial pattern than the range of values in the first in the bare ground point cloud. So let's now erase it. Let's get rid of the legends. So you can see here that, again, for many points, we have a very small range. And all those blue grid cells, they have zero range. That means that there was just one point. The other ones have higher ranges, but most of them are really below 1 meter. But there are some areas that are associated actually with a road here, with some man-made features, but also with some topographic features like here that have much higher range, and it can be several meters. So let's just save it so that we can compare it then with the first return data. So we will raise, we will display the first return data and let me just keep the legend again, just for comparison. And so here we still have that effect of that 600 meters, but that really applies only to one pixel. When you look at the data and we can actually query them, let's see what the values are here. So you can see here the range is around 22 meters. Let's query some of these other points. So in most of these areas, the range or the elevation difference is around between 13 meters, 20 meters. Let's see, these are some big trees. 16 meters actually. So what are these blue areas? Blue areas, these have like 20 centimeters. So that's probably very close to ground. This is 15 centimeters. So those would be within the error of the lidar data in this field. It's all 15, 17 centimeters. And if you know this area is from is close to Dix Park, this is the Centennial Parkway, and this is the big field in the Dix Park. So there is just grass. And that's why the range of values is just few centimeters. So now we will import the orthophoto so that we can associate these big ranges with the land cover that we can see in the orthophoto. Oh, let's just save this. Okay, so this is our orthophoto, and I don't need to run the Rust, it's already displayed. And what we will now do, we will display the first return range over this orthophoto. So remember, here we have some forested areas, another forested area. So when we display, and I will just do it by switching the, let's just do it here, because we will display just a subset of the range. Okay, let's just do that. And let me switch off this. Okay, so here with this command, we are displaying only the range that is greater than 10 meters. So we assume that there is a we are trying to see whether this large range above 10 meters represents vegetation. And when you display this layer over the orthophoto, you can confirm that yes, that's the case. We can change the opacity level to see a little bit under. Okay, so now you can see it quite nicely that there are trees along this road, and within this is actually, there is a stream here, so it's stream buffer and some hill slopes, so all of that is covered with vegetation. So we can save this for our report. Okay, so from all of this analysis, we already got some idea about how the elevation looks like, but none of these DEMs that we have created in a very fast way using binning was really like a continuous raster that would have values for every grid cell. That indicates that we really need to interpolate that DEM in spite of the high density of lidar data, because we want very high resolution DEM, in our case 1 meter resolution. So let's just do it. So we will set the region to 1 meter resolution because we want 1 meter resolution DEM, that we have enough data to create such a high resolution elevation model. And we will use the spline interpolation that we worked with in our previous assignment to compute this digital elevation model. And you will see that this takes a little bit more time because now we are interpolating, we are computing the more complex interpolation function rather than computing just averages for each grid cell. We are also computing the values for many more grid cells, and we get a continuous digital elevation model. Now let's do the same for the first return data. So again, it will, because we are starting with a very large number of points. So first the technique filters out the points, gets rid of the points that are not necessary, that are too close to each other. And now we have again like fully continuous digital elevation model. And to see the structure of the DEM, I will switch off the other layers. We will create a hillshade. So we will use the command r.relief both for the bare ground and for first return DEM. So this is the hillshade for the bare ground. So you can see nicely that we captured the stream channel that is there hidden under the trees that was difficult to see. Oops. And also the road is very, very nicely represented. And let's do the hillshade also for the first return data. So you can see that there is a dramatic difference between what we see on the bare ground and what we see in the first return data. So we have the buildings. This is the state farmers market area. We even can see the cars parking there. So much, much more detail. You can even extract individual trees, for example, here along this road. So let's create some maps for our report. And let me remove the, okay. Let me remove the legends. Okay. So we will now combine the shaded topography with the color DEM that we have, and it's a little dark on my screen, so I will brighten it up a little bit. Maybe brighten my screen too. And then let's add legend. Okay, let me just go back. So this is our background digital elevation model. So let's save it for our report. And let's create a similar representation for the first return data. And let's look at the legend. And what you can see now that I haven't done any filtering with the points, and I got rid of that 600-meter elevation. And what is happening there, that we are using smoothing spline with tension, and that smoothing spline, when you have such a huge outlier, it can smooth out that outlier. So we now have even without filtering that point out, we have now much more realistic digital elevation model. And it's also possible that that point was filtered out just when the data, when the point density was reduced. So let's just save this for our report. And then you have here a couple questions so please don't forget to answer those questions. There is also one additional task that we are asking you to do, and that's computing a map of above ground height of vegetation and buildings. So you have bare ground DEM, you have first return DEM, and now use map algebra to compute the height of all this vegetation and height of all these buildings. So that's all for this assignment. There are some optional tasks such as visualization of the interpolated DMs in 3D, and you can look at the previous videos that are posted in Moodle where this is done, and also the point cloud using +IO.